Welcome. Previous class, I was I discussing on that is spindles, spinels. This spinels, we say that there are two types. Sorry. Two types. That is, one is normal spinels, another is inverse spinels. But we say that this spinels is one type of crystal lattice that is of a general formula, that is AB2 X4. So where this is dicatons and this is tricatons. This we can take that for remembering, you can say Mg into O4, where this magnesium is always +2 oxidation state and is always +3 oxidation state. So this is the general formula of spinels. So here in this case, how many dicatons are there? One dicatons is there and two tricatons are there. Okay, so total 3 catons is present, and here that anion is X4. This is the anions, and these anions can be halogens, that is fluorine, chlorine, and it can be that sulfurs and seleniums. So this can be the halogens, and we see that this is always weak field ligands. Okay, so that we have discussed in the previous class, that catons will form anions will form crystal lattice, and in that crystal lattice the bonds is present. On that bonds these catons will go. So these catons, that bonds can be either octahedral bonds or tetrahedral bonds. Okay, so now these catons, that is, we have that 3 catons. One is A2 plus, another is these 3 catons are there. So from here, that which catons will go to octahedral and which go to tetrahedral, that is decided by the CFAC. So what the CFAC says, that if it has high CFAC, so octahedral, that high CFAC will go to octahedral bonds, and low CFAC other will go to the tetrahedral bond. Okay, so this is the low CFAC will go to the tetrahedral bond, and this octahedral generally large size. So here, and this is generally small size. So in octahedral bonds 2 catons can fit, and here 1 catons, because total is 3 catons. So here, from here, that if the CFAC of tricaton is high, let's say CFAC of tricatons, that is B3 plus, is high, then this will come to here. CFAC of tricaton is high, then it will comes, and this is that this can fit 2 catons, so 2 will comes, then another A2 plus will go here. Okay, now if this is happened, then this comes in the normal spinels. Now let's say, suppose CFAC of A2 plus, that is dicaton, is high, then it will come to this octahedral bonds. Then we see that here 2 catons can fit. Okay, but we have only 3 catons. One is A2 plus, another is B3 plus, another is B3 plus. So one is high, that's it come. Then B3 plus may be low. Okay, that this is the low and this is the high CFAC. This is have that low CFAC and this is have the high CFAC, because this is the same. Okay, this is high CFAC. So if it is high CFAC, then it will come to this one, and but here it can fit 2. So another, it will definitely come another one, because here 2. So now it will be B3 plus. So here again B3 plus. Okay, so this types is there. Then this is called inverse spinels. So these things we have discussed in the previous class. So also we say that crystal lattice, this bonds is formed by the crystal lattice, that is X, Okay, and this is generally that FCC lattice, and this crystal is generally for spinels is always weak field ligands. Okay, so now we will discuss that how by using that CFSC how we can determine that octahedral and tetrahedral with examples. Okay, so let's say one side I am writing normal spinels. Okay, so before this what I said that wherever this transition metals complexes, so the electronic configuration, so since this because that the crystal lattice is formed by the weak field ligands, because the crystal lattice formed by weak field ligands, so this crystal lattice is formed by weak field ligands, so always high spin complexes will form. Okay, so since only high spin complexes will form, so we will not discuss about low spin complexes, not discuss about low spin complexes. Okay, so only high spin complexes will form because the crystal lattice is formed by weak field ligands. Okay, so for this that electronic configurations can be D0, D1, D2, D3, D4, D5, D6, D7, D8, D9 and D10. So any of these can be possible for that electronic configuration for this transition metal complexes. Okay, so out of, because only we are discussing about of that high spin complexes because ligand is weak field ligands. So from here that while you are calculating that CFSC for because for deciding that normal spinels and inverse spinels, we have to say that which CFSC is high. According to, we will decide that whether it is normal spinels or whether it is inverse spinels. Okay, so for this that for transition metal complexes, these electronic configurations anyone is possible. So what I says this D0 configuration CFSC is always 0. Okay, because here we see that, so here we say that here we multiplied by 0.6, here we multiplied by minus 0.4. Okay, so any electronic configuration that D0 means no electron is there, so that is 0, and for this case that is multiplied by minus 0.4, so this will go into minus 0.4, and this is going to get minus 0.8, and this is going to get minus 1.2, and this is going to again one electron will enter here. This is case of D4, so that 0.6 will add, so this is going to minus 0.6, and this electron configuration is going to be 0, and this is going to be that is 2 will add, so this is another will comes, so this is again going to be minus 0.4, this is again going to be that is 2 will added, so this is again minus 0.8, and this is going to again minus 1.2, and this is the electron configuration set again going to be the minus 0.6, and this is going to be again that 0. So these are that CFSC can possible for this possible electronic configurations for a transition metal complexes. So from here we notice that for D0, D5 and D10, this case that CFSC is 0, and also for this case like D3 case, you see that CFSC is highest. The same things after that again this is a decrease here, so this case and this D8 case, so this case that CFSC is highest, and this case the CFSC is the lowest. So from here we notice that what we said, okay, another point, for non-transition metal complexes, here that CFSC is 0. Okay, so if non-transition metal like any main group elements, any main group compounds, the CAPC is 0. So if that is, so we say that for what we say, we say that spinels can be normal spinels, or can be the inverse spinels. So for normal spinels, that we say that B3 plus cations has to be that high CAPC. Okay, and this for and inverse spinel, definitely A2 plus will comes, and this is the 2B3 plus will come, because one octahedral words there has to be and this is at octahedral words. Okay, and this is at tetrahedral words. And what we say that for normal spinels, this has to be that, and A2 plus, and this is the for sorry normal spinels. So what we say that B3 plus and another B3 plus has to be at octahedral words, and A2 plus has to be tetrahedral words. So this case, this is the normal spinels. And the inverse spinels, what that A2 plus has to come to the octahedral words, and octahedral word 2 can fit, so another B3 plus also it should be come, that is A2 plus and B3 plus and B3 plus, so one has left, that comes to the tetrahedral words. So if it is comes, then that is the normal spinels. And what we say that CAPC says that octahedral and tetrahedral words. So if any ligands that have that high CAPC, then that will come to if any metals, if it has that high CAPC, sorry, so what I say that generally octahedral words is larger than tetrahedral words. So if CAPC of any cations, that is here A2 plus or B3 plus, has high CAPC, then it will be in octahedral words. Okay, and if it is low CAPC, if it have the low CAPC, then that will go to the tetrahedral words. That what it says that. So so from here we notice that for normal spinels, that CAPC of octahedral let's say so what it says that CAPC any, like let's say that B3 plus cations, if it has that high CAPC, or we can say like CAPC of octahedral, we will calculate for octahedral, it is greater than A2 plus CAPC of octahedral, then this will be that then this will falls in the normal spinels. Okay, this is the first point. And second point, if that A2 plus CAPC of octahedral is greater than B3 plus CAPC of octahedral, then it comes to the inverse spinels. So why I am talking only CAPC of octahedral case, not tetrahedral case? Why? Because we see that the CAPC of octahedral, that is delta naught, is always greater than that delta T. Why? Because we know that delta naught is equal to 4 upon 9 delta naught, that is delta T. Okay, so this delta naught is very high than delta T, so we will check only for octahedral CFAC, and if octahedral CFAC of this cation is greater than the octahedral CFAC of this one, then this will B3 plus is going to that is octahedral birds, and if it is going to octahedral birds, then this is called normal spinels. Okay, and if it is greater, that CFAC of octahedral of this is greater, then this is going to the octahedral birds, and this will go to the tetrahedral birds. In that case, this will be the inverse spinels. Okay, so why we are checking only octahedral CFAC, not tetrahedral CFAC? Why? Because you see that first thing is that the relations between here, we understand that the delta node is very greater than delta t, nearly that is double. Okay, and we see that whenever you compare that, let's say I am comparing with B3 plus cation and A2 plus cation. Okay, so first I am taking that here octahedral of CFA octahedral case, here also I am taking the octahedral case. Okay, now this tetrahedral will be, this is smaller, so let's say it is smaller value and it is smaller value. So now that any one CFAC is higher, then that will be the in octahedral birds. Okay, so for this case, if I calculate the CFAC, then this is greater than this, then this must be greater than this, because this is greater than this octahedral, then this must be greater than this. So if you know that only the CFAC of octahedral is greater, then obviously this is greater than this, so we no need to calculate the tetrahedral. So we only calculate that CFAC of octahedral. After that, if it is high, then that will go to the octahedral birds. Okay, so we will understand more if we discuss the examples. Okay, before going to examples, let's me some points. So since here that ligand is weak field ligands, that is always for spinels. So only high spin complexes for. Okay, so now that if that B3 plus, this is high CFAC, then it will go to octahedral, and on that case, this is the normal spinel. So if it is has that CFAC of D3 and D8, this is the generally the high CFAC. We see that D3 and D8, they have the high CFAC. So if that any metals, or if that B3 has the configurations of D3 or D8, then this is always go to the another maybe other it may be any other configurations, but if B3 plus has this configuration, this is always from the normal spinels. Okay, and third case, if we say that A2 plus has these configurations D3 and D8, then that is going to be always inverse spinels. Okay, now for case that if let's say B3 plus has that any configurations like D1, D2, D3, sorry, D3 is, then that is always, so D1, D2, let's say D4, D6, D7, D9, this case, and other, and A2 plus has the configurations like D0, D5 and D10, then this is also, this CFAC is always greater, this is CFAC 0, and this CFAC some value will get, so this is again we form the normal spinels. Okay, and reverse is inverse spinels. If A2 plus is this and B3 plus is this, then that is going to be the inverse spinels. Let's say if A2 plus has this configurations and B3 plus has this configuration, then this is going to be the inverse spinels. Okay, and this point is very important, that is if both A2 plus and B3 plus are non-transition metal, then both the cases CFAC is 0, so on that case both are normal spinels. So this is normal spinels. Okay, so if you remember these points, then we can easily solve that the examples of spinels. Okay, so let's take some examples and solve it. The first example is, let's say we have that manganese Fe2 O pore we have. Now we want to check that whether it is normal spinels or inverse spinels. How will you check? Hmm. We will not take these examples. Let's take MgAl2O4. This is the first example. Let's say example 1, and we have that examples like, let's say MnCr2O4 is there, and examples like we have, give me just a minute. FeCr2O4 is there. Another examples, that is let's say we have the examples of Zn Fe2O4. So now the check which are normal spinels and which are inverse spinels. So how will you check? So here that we will took that this is always plus 2 oxidation state, this is always plus 3, this is plus 2 and this is plus 3, this is plus 2 and this is plus 3, this is plus 2 and this is plus 3. So here you see that both are non-transition metal complexes. So both are non-transition metal complexes means their CFS is 0. So this is always normal spinels. Okay. For this case, manganese 2 plus, that is going to be D5, and it is going to get that is D3. So if any is D3, this is like B3 plus is D3, then this is always going to be the normal spinels. So no need to check that CFSE, no need to calculate the whole CFSE. Okay, we can calculate CFSE. It has CFS is minus 1.2 delta knots and its CFS is 0. So this is greater, then that is going to be the normal spinels if that B3 plus is greater. Okay. So for this case, this is D6 and this is D3. Okay, again this is D6 and D3. If it D3, then it is D3 or D8, then again this is normal spinels. If this 3 plus cation, that trication is D3 or D5, then again always that is normal spinels. Okay, for this case you see that this is D10 and this is also D5. So both cases CFS is 0. On this case, what you see that if that size is comparable, then we can say normal or inverse spinels, and if size is not comparable, if size is very much similar, then on that case we will discuss other type of spinels, that is mixed spinels. So if that size is comparable, on that case if size difference is there, on that case we can distinguish either a normal or inverse. But if size is also same, nearly same, on that case we will discuss about another type of spinels, that is mixed spinels, because both the cases CFS is 0. So next is to characterize by the spinel by the size. So you see that for D block, that is from left to right, size is decreases. It means that Zn2 plus and Fe3 plus. For this case, what you see that left to right size is decreases. So Zn2 plus will be here and Fe2 plus is somewhere here. Fe2 plus or Fe3 plus, this size is very decreases. So you see that this size is very low. Okay, this size is high compared to this. Although this is 3 plus, but still that is size is, this is greater. Okay, so if this size is greater, then greater size will go to the octahedral buds. So octahedral buds means that is normal spinels. Okay, that's how we can check that inverse or normal spinels. Now we will discuss the third type of spinels, that is mixed spinels. Mixed spinels are, on that case, it is possible when that CFS is 0. If CFS of both have 0, 0 and 0 and they are and both not and if CFSC of both have 0 and both A2 plus and B3 plus should not be non-transition metal complex. If both are non-transition metal complex, on that case that will be the normal spinels. Okay, that we have discussed. So if they have if both the CFS is 0 and the size of A2 plus and B3 plus are very much similar, then on that case this will be for mixed spinels. Okay, so example is that is manganese Fe2 plus copper. So in this case this is also having that this is plus 2 and this is plus 3, this is D5, this is also D5. So both the case CFS is 0 and the size of this Fe2 plus manganese 2 plus and Fe3 plus are nearly same. So we can't distinguish by size. On that case we say that this is a mixed spinels. Okay, this way we can say that which are mixed spinels and which are normal spinels, which are inverse spinels. Okay, so for normal spinels, what we say that if that B3 plus cation has high CFSC, then A2 plus cations, then that is going to be normal spinels. If A2 plus has that high CFSC, then B3 plus, that is going to be the inverse spinels. Okay, and note that we are only calculating that octahedral CFSC because octahedral CFSC is generally greater than tetrahedral CFSC. And note that this. So whenever we are seeing that this case here, that whenever it is going to the octahedral bonds, B plus is going to octahedral bonds, then that hybridization for octahedral bond is sp3 d2 or d2 sp3. So for this the hybridizations will be sp3 d2 or d2 sp3. For this tetrahedral, that hybridization is sp3. So for normal spinels, the hybridizations are sp3 d2 and sp3. Okay, for octahedral bonds and tetrahedral bond this, and for this also octahedral means sp3 d2 or d2 sp3, in this case sp3. So sometimes that hybridizations they will say, from that also they want to confuse you. So if that B3 plus is going to octahedral bonds, then that hybridizations will be sp3 d2, and similarly if A2 plus is going to tetrahedral bonds, tetrahedral means its hybridization is sp3. Okay, now we will discuss one points, that is that final parameters. Final parameter, that is this is equal to number of B3 plus cations in tetrahedral bond upon total number of B3 plus cations in lattice. in lattice. Okay, so let's say we have that two, that spinels are one is normal spinels and inverse spinels. Inverse spinels, two cases are possible. One is complete inverse, another is partial inverse. Okay, so what you say that now spinal parameter is number of B3 plus curtains in tetrahedral buds upon total number of B3 plus curtains in lattice. So here we say that for normal spinels, that all B3 plus curtains is in octahedral buds. So no B3 plus in tetrahedral buds. So that will be parameter is going to become 0 upon 2. So that is going to be, this is 0. So here that lambda value is 0 for normal spinels. Okay. For inverse spinels, this lambda will be for complete inverse. For complete inverse, lambda will be, that is lambda is equal to number of tetrahedral buds B3 plus in tetrahedral buds. So inverse spinels means that one. Here we see that so for normal spinels, one B3 plus will be definitely in octahedral buds. So what is here, that one will be in tetrahedral buds, 1b3 plus 1, and total is 2. So this is going to be 1 upon 2, that is equal to 0.5. Okay, and for this final spinels, that will be if so partial inverse, that will be that lambda is greater than 0 and less than that is 0.5. So if that parameter, the spinal parameter is in between this, then that is going to be the partial inverse spinels. Okay, so that's how we will distinguish by the help of spinal parameters. If spinal parameter is 0, then that is normal spinels. If that is half, then that is called to complete inverse, and if it is lies between 0 to 0.5, let's say 0.4, that is the inverse spinels. Okay, so today after this, in next class we'll discuss on questions and answers. Thank you.